So, yesterday finally we started with the, I would say, physics proper of long-range models, discussing equilibrium properties, and in that case finite temperature equilibrium properties of long-range systems, and saw a number of peculiarities that really distinguish them or make them in some cases also richer than short-range models. And for the first half of today's lecture, I continue with that in that direction on equilibrium physics, but we're going to look into quantities that are more quantum than what I discussed yesterday. That is quantum phase transitions of long-range models, and then hopefully in the second part of today's talk, we'll be moving on to non-equilibrium physics or dynamical properties of long-range quantum systems. So we're getting away from equilibrium then. So if my numbering is correct, that should be 5.2. Equilibrium quantum phase transitions in long-range models. I would assume that you have at least some idea of what a quantum phase transition is. Some of you certainly do, but I'll mention a few things. So I'm not going to explain the concept in great detail here, but for those who have not encountered it, I'll give a few hints of what it is about, and hopefully enough so that it's clear what this is about. So quantum phase transitions are phase transitions that occur at t equals 0. So it's about ground state properties of models, and at the phase transition point, you have drastic, like non-analytic changes in some interesting quantity in the system, and in finite system phase transitions that happens usually when changing the temperature as a parameter. And here we have transition upon variation of a Hamiltonian parameter. So I only write parameter here. So it's a parameter that is in the Hamiltonian, and we're asking the question, when changing something like the field parameter in the Ising model we had before, how does the ground state of the model change? And this is the situation we are looking at. And similar to thermal phase transitions, we have features that we are familiar with from phase transitions. So we have critical exponents, universality classes, and so on. So this appealing feature of having properties that are shared by large classes of systems, I mean, not only properties, but like numerical values of certain exponents or scaling functions, this we also have for these quantum phase transitions. And then you would say at t equals 0, is that physically relevant? Well, the important point, of course, is also that if you have the proper phase transition at t equals 0, so the sharp transition in ground state properties, when probing the system at finite but low temperature, you can also detect signals of that quantum phase transitions, and these can be very characteristic, and this is what people probe in actual experiments. And the standard reference, if you want to look this up, is by Sachdev, which is a book, which has quantum phase transitions as its name. There's a large body of theory here that I'll not go into, but there is an important signature of a quantum phase transition. So what do you look for in a certain model to say, here I do or do not have a phase transition? There's not exactly a one-to-one correspondence between this signature and the occurrence of a quantum phase transitions, but it's really a fairly easy thing to look at, and for at least a continuous quantum phase transitions, in most cases it will do the job excellently to detect a quantum phase transition, which is the gap closure. So we're going to look at the spectrum of the system and the spectrum in many cases of a model we are looking at will be gapped from the ground state. So we have ground state, then a large, then some gap, and then a spectrum that in the large system limit kind of becomes continuous. But when we tune the parameter to the phase transition, this gap will close. And the way in which this gap closes, like the functional dependence on the parameter of the gap closure, this is, contains lots of information about the quantum phase transition. So in terms of calculations, what we're really going to do now, we are going to look at a long-range model and investigate how the gap of that model behaves when changing a parameter towards a phase transition, and study the properties by studying the gap closure of that model. Right. Our model of choice for this chapter will be a different one than before, so I'm not going to look at transverse field Ising model now, but at a model that is strongly inspired by the transverse field Ising model. And so it goes under the name of Kitaev chain, and it's a very simple one-dimensional model, and I will give you, for those who haven't seen the model, I will give you a brief motivation where it comes from and how it's closely linked to the transverse field Ising model. So I told you about the nearest neighbor, so NN is for nearest neighbor, transverse field Ising model, that it is exactly solvable. And the way you do this is you first do a Jordan-Wigner transformation, which is a transformation that maps spin 1/2 onto fermions, onto spinless fermionic operators. And so, and when you do this, you'll find the transformation, if you haven't seen it in many textbooks and so on, it's really easy to find under the name Jordan-Wigner transformation. I'll tell you how the fermionic Hamiltonian looks like that you're getting to. And so step is Jordan-Wigner transformation, which maps spins onto fermion operators, and then the resulting Hamiltonian looks something like this. So there is a hopping term, Ci dagger, Ci plus 1 plus Ci plus 1 dagger Ci. And then there's a term that is called the pairing term. Looks like this. So now this is still all nearest neighbor that I'm doing here. Ci dagger, Ci plus 1 dagger plus Ci plus 1. And then we can have a chemical potential here and a Ci dagger Ci. This term here I called a pairing term. It may remind you of something like a BCS Hamiltonian, where you have these occurrences of pair creation in some way. And this is what you get when you do this transformation. And now one could say, well, this is the Kitaev chain. So let me write the name here. Now this may sound now like a stupid idea. Why do I give a new name to an old model only after doing a transformation that many people have done before Kitaev? This sounds like he didn't do much to earn that this model is named after him. Well, he actually did, because even though it's the same model, meaning it has the same spectrum as this model, now it became a very interesting model because what a local operator is, or what a site is in this Hamiltonian, has changed compared to the Ising model. So when you do this map, this Jordan-Wigner mapping, this is a non-local mapping. So different sites will affect what becomes the new site of the Kitaev chain. So now this notion of locality has changed, and this model, the Ising model, had a regular phase transition with a order-disorder transition, and because of the non-local transformation that led here, what was the local, the usual order parameter in the transverse field Ising model is now a non-local parameter here, or if you want, and it has the it shows a topological phase transition. So same model, different interpretation because it has a different notion, or it changes what was local in the previous model and what is local here. So it's very interesting to look at, and there's Kitaev's original paper that started this, and it's quite some literature has accumulated on this topic. I'll not much go into this direction, but what I want to do now, I want to promote this model to a long-range model. So first, let me say, because the models have the same spectrum, the quantum phase transition that the nearest neighbor transverse field Ising model has, of course, is inherited by the Kitaev model. Same spectrum, same quantum phase, same gaps and or gap closure that we have. So we have a quantum phase transition here, and now what we want to do to change this and make it long range, and I'll show you in which way I'm going to do this, and then so
this is a Kitaev chain as opposed to a Kitaev model.
Yes, so there's also a model that is usually in two dimension with these what is it, hexagon or structures in the lattice. This is a different thing, and it's really a lot simpler even than that model, but similar to other things that Kitaev did. He studied this to look at topological phase transitions and topological properties.
I think we could change the order.
The second one, CI plus 1 CI.
Yeah, you're absolutely. Thank you.
So one question, the Kitaev model has been promoted to the one with long-range interactions. I mean, promotion is not a big deal, but I guess people have studied.
I actually thought about something I wanted to discuss with you at some point, and it goes in this direction. But I was thinking about this afternoon discussion here. So I believe it hasn't, because it doesn't have. Well, it has these kind of plaquette type interactions which make the question of what long range is a bit more difficult, but it's something interesting point.
What's the commutation relation with the AA and
Oh, I couldn't hear you now.
what are the commutations that the AA and
Fermionic, so fermionic anti-commutation relations. Yeah, and these are spinless fermions, so there's no spin degree of freedom associated with them.
what about site I and I plus index I and I plus?
Well, different sites anti-commute. Yeah. Okay, how do we do long range now? I'm gonna promote the pairing term to long range. I could do both, like also the hopping term. It does not change the physics. It only changes the location of the critical point, and it will make our calculations a little bit easier to only promote this to long range, and we will not lose any physics. So the difference is really trivial here at this point. So I'm going to do what is easier. So I'm sorry, I do some wiping here now, which is, I know you can't do this in your notes, but so my notation here is this is a sum over all pairs ij, all distinct pairs, and then this here will look similar. So we have ci dagger cj dagger plus cj ci divided by I minus j to the alpha. Right. We will use periodic boundary conditions because it will make our life easier again. before we get to this, a general comment. So this long-range extension of the model is not equivalent to making the transverse field Ising model long-range. This is so when you make the transverse field Ising model long-range and then try to do a Jordan-Wigner transformation, you don't get a nice simple Hamiltonian like this one. You get something substantially more complicated. And so why we now do the long range in here is because it keeps the model stays so simple. And by simple mean everything is quadratic in creation and annihilation operator. And when you have any Hamiltonian that is quadratic like this, there is a transformation with which you can diagonalize it. This is, I mean, you certainly have all seen the Bogoliubov transform, which is usually in low-dimensional subspaces of the system, but even if you have disorder here and anything complicated, there will be, for such a model, a matrix diagonalization of size 2n by 2n, which will diagonalize this Hamiltonian. That is good to know in principle. We're not going to do this general thing, but we're going to make so now our goal is to diagonalize this model.
So the transverse field, when you make it long range,
yeah.
can you still do Jordan-Wigner?
No, the transverse field Ising model. When you make it long range, well, you can apply the transformation, but you don't get a nice quadratic Hamiltonian. I mean, a transformation you can of course apply. Yeah. It gets very ugly. Yes, it gets ugly. People have used it for long-range models and then truncating it in some way because you get very you drop terms of some level of complication, and you can use this as an approximation that for large value of alpha you can expect to be reasonably good, but how to interpret this, I think that the Hamiltonian, depending on the parameter, has a tendency to have fermionic pairs at sites of a certain distance. Right. There would be a general transformation, as I said, like some matrix diagonalization that would diagonalize this, but to make our lives easier, what do we do with such a model? What's the first step?
Why do you make long range the pair hopping and the anomalous term and not the...
Not this one. Oh, I mentioned this briefly. I could do this as well. Physics stays the same, but the location of the critical point would be affected. With this change, it's not affected, which makes my life easier in the computations to come. That's it. Yeah.
One thing out of curiosity, I have this amendment. So if I go back now to the speed picture, what does it look like? Do you have any idea?
So this I haven't tried out on paper, but because the Jordan-Wigner has these Jordan-Wigner strings, which are the objects that make it the transformation non-local. I assume that you must get the same also in the spin picture, that you will have some terms that contain very many of spin operators, so like not pair interactions, but something that involves very many operators also in the spin picture. Well, this is from reasoning, but I haven't tried the back transformation. Yeah.
The interaction, I think, increases from a 2 per interaction.
Yeah. These are the ugly terms you also get when transforming the long-range Ising model to the fermionic language. You will get these ugly terms that contain many, many fermions, these strings of operators, and the same must happen the other way around as well. Okay, this here we want to solve, meaning we want to diagonalize the Hamiltonian in the and instead of a general transformation, I told you I would use periodic boundary conditions, so this must trigger your reply that we do a Fourier transformation, right? I mean, translation invariance, there's no way. We do a discrete Fourier. So we replace a Cj fermion. I use the square root convention for the Fourier transformation, and then we have e to the minus ij k a k. Yeah, no, I is always a confusing choice, so now this is, of course, the imaginary I. I'm sorry for that. And the k's are from the Brillouin zone, so should I write? Let me write it down quickly. K takes values 2 pi small n divided by capital N, and n is from Zn, like a natural number up to n. Right, this is what I do. I'm not going to go through the algebra with you. I'm sure you have done something of the sort. I'm going to tell you how the Hamiltonian looks like. And I'm going to write it in a matrix form, but this is just a convenient convention to express all these quadratic terms as a vector times a matrix. Oh, sorry, let me can I erase this? Yeah. A vector times a matrix times another vector, which is just a way of writing all the possible combinations of the creation and annihilation operator. J cos k plus mu minus j cos k minus mu, and then I delta and a function f of k, which I'll define in a second, and minus I delta. If we had done the diagonalization for the short range model, we would, well, this is plus k, so plus mu. If we had done this for the short range model, we would have the cos k here and the sine k down here. And now the long range has modified the sine k to this other function, which inherits kind of the long range properties that we have here. So it's some L1 to n half. I assume n to be even here, otherwise you get some, it's almost the same. Sine k L divided by L to the alpha, yeah. I have minus alpha in my notes, but yeah. All right, this is what we get. Just as an information, we're not going to use this explicitly, but there is a way in the large n limit, this here can be expressed as in terms of so-called polylogarithmic functions. And the advantage is knowing this, that when you have the expression containing this function and you want to do numerics, say with Mathematica, it will be a lot faster because these functions are available in Mathematica. And if you want to do asymptotic analysis of the result, then you will have, you can use known properties of these polylogarithmic functions. So in the large system limit, we have an advantage that this becomes a known function. All right, so what we see now is that the remaining task is to diagonalize these 2 by 2 block Hamiltonians here, and then I mentioned already the word how we do this. This is now a regular low-dimensional Bogoliubov transform that you can use to diagonalize the remaining term. And diagonalizing only means to bring it in the whole Hamiltonian into the form of a sum of harmonic oscillators, yeah. Good. remaining task, Bogoliubov. There is a constructive way of constructing how exactly the transformation will look like. I'm going to tell you what the transformation is. You can verify that it does the job, but you can easily look up how to start with this Hamiltonian, write down some equations that you solve, and you obtain the exact form of the Bogoliubov transformation. But I'm not going to do this here now. My Bogoliubov fermions, to which I transform, I'll call eta, and eta k dagger, eta minus k dagger, I'll write it down as a matrix transformation, and they are given by some matrix applied to ak dagger a minus k.
Is there an extra dagger?
Yep, thank you. And these guys here are called the Bogoliubov angles. So this rotation, if you want, in the space of these fermions brings me to the new ones, and the rotation angle is given by tan of 2 beta k's. So beta k is what we want to determine with this equation that I'm going to write down now, minus delta f alpha k divided by j cos k plus mu. Yeah, if you don't want to do the constructive way, just take this definition, plug it into the above expression, and I'll tell you our final result of this calculation for now. Then we have a result that where we can discuss some physics. So as I told you, the goal is to get a Hamiltonian that is essentially a sum of harmonic oscillators. So our final result looks like this. Not only here, but also earlier on, I might have dropped constant terms in the Hamiltonian at times. So whatever is constant, I forget about. Yeah. Yes, please. From the Kitaev chain, there's no approximation. No, this is an exact solution. I mean, it's a quadratic Hamiltonian. We can solve it exactly, and this is only transformations, no approximations here. Oh,
How did the delta and mu arise?
In the delta and mu are functions of the coupling constants of the transverse field Ising model. I haven't written down here what the functional expression is. No, I would need to check this, but it's actually a warning. What I call here J in the Kitaev chain is also, it's a function of the old J of the transverse field Ising model, but it's not the same J. So bad notation on my side, but it's something like the old coupling minus 1 or divided by something. So it's very simple expressions of the old couplings. Sorry again? Lambda should? Lambda has a k dependence. This is our main object of study now. So this is what we're going into. Lambda alpha of k is the dispersion relation of this model. So the connection between energy. So it gives, for a given momentum, it tells me what the corresponding energy is, and the result is 2j cos k plus 2 mu squared plus 2 delta, and then we have this function f alpha of k in here, and the square root of the whole thing. Right. This is our main technical result of this chapter. So this is the diagonalized version of the long-range Kitaev chain. And now, as with all these free fermionic models, as they're called, so those that can be mapped onto a bunch of free fermions with some dispersion relation, now all the information about the physics of the model is contained in this function here. That's everything we need to study, and this is what we're going to do now. And as I said, it's going to be about the gap closure. So the question is going to be when this function here and for which values of k and what values of the parameters it can become 0.
So for this model, so yesterday you had made a couple of, maybe there were 3 comments, like the behavior of transverse field, how does it change when you introduce a long-range coupling, like there is this alpha between 0 and 3/2 between which it remains mean field, etc. Those things can be studied for this one? Those aspects?
So what?
The mean field solution, how long does it remain valid, and the critical exponents start to get modified?
This can also be done here, but remember the plot of the critical exponents that I showed yesterday were critical exponents of the finite temperature phase transition.
Yes, sir.
Now, in this model, this model does not have a finite temperature phase transition. So that's also one of the remarks I would have done towards the end. We will see that this model has the long-range version of the Ising model can have a phase transition, as we have seen. The long-range model of this long-range version of this model does not have a thermal phase transition. This is also the reason why this model is simpler than the transverse field Ising model in the long-range version. I had to use the Ising model for yesterday's topic, and for the quantum phase transition, as I said, my strategy here is I use the simplest model where I can see the interesting physics. So today we can get away with the Kitaev chain. Right, so our task now is to analyze this dispersion relation, and let's first, when I have just finish the sentence. When I have a result, the first thing I do is not a complicated calculation, but a plot. So we're going to look at a plot now. You have a question, please.
If you made the hopping term long distance, then what change would be there in this lambda?
The cosine would be replaced by a function like this as f alpha, but with sine terms. So the cosine k would be replaced by g alpha of k, which is a sum over L to n half with sine kl divided by L to the alpha. That would be the whole change. Right, let's look at a plot. No, this we have done. Right, here it comes. All right, so what is shown here? I didn't put labels to the axis. I don't let my students get away with plots without axis labels, but this one doesn't have any. Okay. So this here is k, the lattice momentum, and I did this plot in the large n limit. So I used for this function f alpha here the polylogarithmic function, which is like the n to infinity limit. Otherwise, in this expression, n doesn't really appear anymore. So the only difference is having discrete values and replacing this f by this polar logarithmic function. All right. I use the convention where I look at lattice momenta between minus pi and pi, and then I just plotted this function lambda that I showed here for different values of alpha, and of course I use some smaller and some larger one. If you look at alpha 7/2, so 3.5. Well, this is just at some value of the chemical potential, not a specifically chosen one, and you see that the spectrum is gapped away from 0, so it does not go, in this case, below 1. So this implies that at this point, mu that I chose here, this does not look like there's quantum phase transitions, because otherwise we would have been down here at 0 with the values, right? No phase transitions, just a regular value. And then the alpha equals 3/2 looks more like a regular dispersion relation, like some function. Very often it looks a bit sine or cosine-like, something like this. But the difference we start to differences we start to notice when we look at smaller values of alpha, where the smooth-looking behavior here is replaced by something that has a kink at the value alpha equals 3/2, and that becomes divergent at the origin at alpha 1/2. And these values, as you can imagine, represent, of course, the cases alpha smaller than the dimension that I'm interested in, alpha between the dimension and 2 times the dimension, and alpha larger than 2 times the dimension. In the spirit of the plots I showed you yesterday, where the behavior and the critical exponents and the presence of a phase transition and so on changed in these different regimes. This is what we are looking at here. So now, okay, this was just some random value. Everything looks, well, the larger value of alphas look familiar if you have seen a couple of those dispersion relations. The smaller ones, having a kink and this divergence, look uncommon. This is something that you do not usually have, and you certainly do not have in the short-range Kitaev model. So something has changed here. Yes, please.
What does that divergence mean in the dispersion relation?
So, I mean, of course, in the simple sense only, there are k values at which you have a very high energy. I mean, the divergence you really have then only in the thermodynamic limit, of course, because otherwise you will have discrete values somehow taken on there. But there is an interpretation of the dispersion relation in terms of the group velocity. So when you calculate the group velocity of a model, you would usually look at the derivative of the dispersion relation close to 0 or at 0. So you in this model already for alpha equals 3/2, the group velocity would become, no, I think here it's not yet divergent, but it would become a divergence. So I'm not sure how well this interpretation can be used here, but the conclusion here would be that the group velocity, something that has to do with the propagation through such a system, becomes divergent and become extremely fast. And actually, this is something that will coincide with something we hopefully can have a look at tomorrow when we look at non-equilibrium systems. So I'm not going to look at dispersion relations tomorrow, but sorry, let's go back. But we will find that models with a very small value of alpha can have very fast and in some sense infinitely fast propagation of certain properties across the chain. So I believe that there is something to this interpretation of the group velocity. For the quantum phase transition at the moment, the divergence doesn't have really any particular meaning, because we are looking at points where the gap closes, and there's no gap closure associated here at the moment.
If you had put a Katz's kind of normalization,
Yeah.
then this divergence should still be there, or
There, the hang on. Yes. The no, how was it? No, the infinite slope would still be there, but the divergence you lose when you do that. I think that's it. We get to the discussion of including the Katz normalization hopefully in a second. Yeah. But it changes exactly around this point there.
Sorry.
Yeah.
So if you compute 2-point functions
Yeah.
at different times, you will probably see the effects of this dispersion, right? Correlation function.
Correlation functions at different times. So you want to look at something that has to do with propagation. Is that what you're saying? Yes, you do. So I would say with my preferred tools, I would compute Lieb-Robinson properties, which are
Which is the same.
essentially or closely linked to two-point correlation functions, and you see that this happens. Yeah. So what I'm trying to say when I answer this question is, there is something that is like the group velocity diverges. I'm not sure how close this interpretation of what I see in a Lieb-Robinson bound or in a two-point correlation function is to looking at the derivative of the dispersion. I'm not sure how closely linked these two things really are, but it's consistent for sure for what one finds here.
so what delta and j values are you choosing for this plot?
What delta value? I'm sure I used 1.
For j as well?
Yes. Yeah. Delta and j are 1 here.
So what's the conclusion from this plot?
Well, at the moment, the conclusion. So this is not the most interesting plot. I hope I'll show you more interesting ones in a minute. The conclusion here is that at the origin, so at momentum 0, something unusual happens for the very long range cases, which are these kinks and divergence of this property. And now we get to the values where we have a quantum critical point, and you'll see that the quantum critical point, there is one at 0. So there is a quantum critical point at another value of the field that explores this funny behavior of this dispersion relation. So our quantum critical point will inherit the weird behavior of the dispersion at this point. This is where we're going to get to. So
So when you are computing this lambda alpha of a,
this here?
yeah, so when you are putting the square root, don't you think that you have a plus minus as well? Like you have two bands?
No.
You should have, right, when you are taking square root.
No, but I would have too many. Sorry, the Hamiltonian is?
Depends on the range of phase. Here he's taking the range of phase in range, so that's why one lambda k is there. So if you dividing,
I think I have all the modes in here that I need in terms of numbers. I mean, I think.
I was wondering, negative solution would have been also a solution.
that is included in the
How to see that actually? That's it.
if you look at the range of
Negative
phase,
solution.
that is the complete range.
No, I think so. I mean, so you were asking about the negative lambdas here.
No, it's
No.
it's not. It's an Ising symmetry. It's
Yeah.
not XY.
Yeah. So at this point, so my logic here would be I have already enough I mean, I have only so many energy values here that I can have in the system, and I have exhausted the number that I have. Maybe that's not the best answer that I can give. So if I would include negative values of lambda as well, I would have twice as many. My spectrum would have twice as many values here as well, which would be too many for the size of the Hilbert space of the system. But I agree that this is not the ideal, this is not the perfect answer. Anyone with a better one?
So for each value of k, let's say 2 by 2 matrix, right? So for each value of k, there should be 2 eigenvalues. That's my suggestion. Yes, there will be a symmetric thing, but I think that those band will have similar features since it's just a negative.
No, I mean, this would just be the negative reflection of the whole thing, yeah.
It can be
Yeah.
just analyzing this also will.
No, but it makes a difference, of course, in the interpretation of what the ground state of the model is, because the ground state of the model should not have any excitations, and only the moment I start to excite something, I'll raise the energy of the model. This is why I'm
So when you talk about the capness of the spectrum,
yeah.
so you need that plus minus to see that whether at k equals to 0 you are getting the value 0 of this lambda, right?
I need what to?
The value of lambda you would be needing to be 0.
Well, I would say.
So that the spectrum is not gapped.
Well, to look at if the spectrum is not gapped, I mean these are mode excitations, right? So I would say if I have this expression and I do not excite any mode, then I have the lowest energy. So this is why no mode excited, energy 0, and this is ground state energy 0.
Maybe I'm getting something wrong. Okay.
Yeah.
Discuss that.
But I also agree that the explanation wasn't. So maybe I'm failing to give the best argument to explain why it should be like that at the moment. I'll try to come up with a better one for tomorrow. Let me. All right. Where are we? Sorry, now I'm a bit, here we go. Okay, this mu was, as we see from here, a non-critical value. So now the simple analysis continues by looking for the values of mu at which this quantity here can become 0. And I mean, this is just a simple discussion of this function here, which we do to look for a phase transition. And let's do it in this order. Okay, first to six. Okay, so we're looking for solutions of lambda alpha k b0, and well, for this to be 0, we need this term to be 0 separately, so it should be at there should be zeros, or we have a chance of getting zeros at a value of k, which I call k0. N is a multiple of pi, with n is some some integer number, and if we use this value and plug it in here, we find that the corresponding mu value is the critical mu is plus minus j, and I'll use j equals 1, so we get plus minus 1 as our critical value here, at which when we set this value to plus minus 1, at the value at values of k multiples to 2 pi, we should get quantum gap closure, and this is the corresponding plot. I picked the one at mu minus 1, which is the more, well, I can tell you why. The one at mu minus 1 corresponds to k0, and the one at mu plus 1 corresponds to k equals pi. But we saw what I claim are the more interesting properties of this dispersion relation are around 0, so I thought I'll choose the critical point mu equals minus 1, where that is related to this k equals 0 point here. So indeed, there's a gap closure is seen here, but not for the value alpha equals a half, where this divergence kills. So at this point, you have made the comment already. We could have cured this by using the Cutts prescription, in which case we would save this critical point and pull these down here and have this transition exist also for alpha smaller than 1. I actually didn't do it in that slide because I wanted to proceed, and then my plan was to ask to the audience the question, well, why didn't we get a transition for these small values of alpha? But you've answered the question already. Thank you. Yeah. So indeed, for observing a phase transition at this value also for alpha smaller than 1, the Cutts prescription would have been a good choice, and it would have given us a transition, something interesting to study also in that case. Actually, the first paper in which this Kitaev long-range chain was developed did not use the Cutts prescription. In fact, found that the transition disappears for values of alpha smaller than 1, and then came up with the conclusion that there is a what is the wording? Quantum phase transition, which is with massive excitations, like with no gap closure and something like this, so that there is a very special phase. And well, you can argue that this maybe is a somewhat misled interpretation or so.
So which is the reference?
It's a, do I have it here? It's a PRL, it's called long-range Kitaev chain with Davide Vodola as the first author. It also has Elisa Alcolesi, whom you might know, as and I think Guido Pupillo. I think that's a PRL from 2014. I'm not talking bad about the paper. It's a good and interesting paper otherwise, but I think at this point they maybe have stronger conclusions than are really needed here. Yeah.
I understand that the divergence comes from the F alpha of k for small alpha. Okay?
Yeah.
But if you show this F alpha,
You're saying that at k equals 0, it should be 0?
no, okay, so I was asking, you had to have an order. You
Yeah.
have to send
Yeah.
limit before taking k to 0.
Yes. So what this f, so it's true. If you take this, the function f alpha, it's a sum of sine functions, right? Where do you have it? Yeah. If you set k equals 0 in here, then of course you will get 0 for the function, and you cannot get a divergence. But what this function really does, it in the discrete version, let me do a little plot. So it is 0 at k equals 0, and in the discrete version it will do something like this, and then go down very sharply, and the larger you make n, the higher you will go and the sharper you will go down. But at this point you have 0. But if you first take a thermodynamic limit of this function, which you do when you choose this polylogarithmic functions in the dispersion relation, then you find something that is a diverging function here. So indeed it has to do with the order of limits. Then you would say, well, it's this one point here, and I mean, it becomes a one point of the dispersion relation, which then is, I would kick it out by continuity if you want. Yeah. All right, where are we? Good. Now we. Okay. Okay, now we know where we do have a quantum phase transition, and at the moment we haven't seen anything specific for long range. As I mentioned, if we had used the long range also for the hopping, we would have had a change of the critical mu, but that's not so exciting as well. But what I want to get into is a change of the critical exponents that is affected by long range systems. So where do we see the critical exponents? And now I have to find the right piece of paper here. So where are the critical properties? Now, hidden in the dispersion relation. And so this is the point where I said I'm not going to do a big discussion of quantum phase transitions, but I'm going to tell you how the critical exponents are linked to the dispersion relation. And they're linked to asymptotic of lambda alpha k, and the following two cases. So one of the critical exponents say that lambda alpha at k minus k0. So k0 is now the value at which the transition occurs, which in our case is 0, so I could have left it out, but I want to give you the more general expression. Behaves asymptotically in this distance from the critical from the k0, like k minus k0 modulus to the power of z. So this asymptotic behavior at the of lambda at the critical point gives us the what is called the dynamical critical exponent, which is one of the critical exponents. And the second asymptotic relation that I'm going to look at is when lambda alpha at the critical value, how this one changes with the value of mu, so mu minus mu c. And the corresponding critical exponent is the combination of nu and z. And nu is the critical exponent governing the correlation length. Critical exponent. So you see, it's quite a simple thing. Calculating critical exponents in such a model really boils down to discussing the dispersion relation, if you have them, like we do in this case. And now we can do an asymptotic analysis and find out what these exponents are. And I think I'm not gonna bore you with the discussion of how of a derivation, but give you the corresponding results. So so now this was the general statement, and now for long-range Kitaev, what we get is lambda alpha k is proportional to k to the z, with z is alpha minus 1 for 1 smaller than alpha smaller than 2, and 1 for alpha larger or equal than 2. And in our choice of model, for alpha smaller than 1, we do not have this phase transition as we have seen there, so there wouldn't be a relation there. And it becomes a bit more complicated to calculate this with the Katz rescaling, but well, now I have to remember, I think if you, this I've done a long time ago and not refreshed for this one, I believe that when you go to alpha smaller than 2, that you remain at 1 from then on, but I'm not sure about this one. But and the second critical exponent is yeah, let me just write this down and then I'm ready for a question. And the other one, also by just discussing the dispersion relation lambda alpha at k0, is j plus mu modulus, which we just get by plugging in this k equals 0 into the dispersion relation. And so this corresponds to mu minus mu c to the power of mu z. So we can read off that mu z is equal 1. Mu z is equal to 1. Right, and so what we find here is in a similar spirit to what we had for the thermal phase transition, that there is a regime of alpha when alpha is sufficiently long range, and it's again alpha smaller than 2 in this case, where the critical exponent starts to change continuously with alpha. All right, so we had a question. Yes.
For alpha less than 1.
Yes.
Then why are we
Because I've done everything for that model now without the Katz prescription. So I just yeah.
What should we believe? What happens?
What should we believe? I mean, look. I mean, if you use this model, this is the phase transition behavior. If you use the model with the Katz prescription, then so now this is something I didn't have time to prepare the Katz prescription version for this lecture, but if I remember correctly, what I have done some time ago, I think the phase diagram was like this. So if we now I'm plotting mu, and I want to do this as a function of alpha. Right. And then we look at +1 and -1. So I'm hoping to give you at least an idea what is happening. So I did not look at the +1 case because this one is a bit more boring in some sense, but it exists also without the Katz prescription. There is a reason to understand where this comes from. It's essentially something like a single. No, I'm not going to try to explain this, but it doesn't see the funny long range behavior here because we have a very regular behavior over there, which is the k value corresponding to this critical point. And on the other side, we found something like this that goes down and it stops at alpha equals 1. Now, if we include the Katz prescription, at least I try to give you the information that I remember from when I did the calculation, actually. So now, okay, this was no Katz, and this here is Katz. Then, of because nothing really changes for alpha. This is again alpha and mu, then down to alpha equals 1, nothing really changes. And then the Cutts prescription starts to mess with the plot. So what now, this point here, in the spirit of what I told you, that the transition in the thermal case runs out to temperature infinity, happens here that the transition is essentially pushed out here. So now what the rescaling does, it pulls the transition back into finite values by this rescaling. And we get something that I'm not sure if it went straight down or it had some other functional dependence. I'm not sure it went exactly to -1, but it goes to some finite value. But this pushing in that you do by the rescaling also happened for this point, which then is somehow pushed. I mean, this is just a very vague sketch. I don't remember what the exact details were, but you end up with both critical points with the Cutts prescription, one being at a finite value and the other being at 0, because the one that did not scale before is essentially scaled to 0 in that case. And about the critical exponents, I believe it got stuck at alpha equal, at this, at the same value that you had for alpha equals 1, but I'm not sure about this. We can try to do it afterwards, but it shouldn't be a big deal to do it, yeah. No, look, it's not about believing. I think both are right, and the question is which information can you read off from them? I mean, it's both. You say you choose this model and you get this and that result. It only when you start asking questions about large finite systems, then you will have a difference in what your interpretation is. So when you say, now you use this, but you want to know something, so if you want to know something about a large finite system, then this one can tell you that for alpha smaller than 1, this transition here, you will be able to find it, or something that is similar to an infinite system phase transition, but the finite system version, you can find it at some super small value of mu somewhere out there. And that this value will in some way scale. So this is the type of, this is the information that you can learn from when you use this here with the Cutts prescription. This here will tell you that in the version with no Cutts prescription, there is in reality phase transition-like behavior for very large system, which happens at very large mu. From this here, this piece of information you cannot deduce. You will not know about the large but finite system behavior phase transition precursor. So both are right in the sense in the limit, but if you want to use them for an interpretation about the finite system, this one can give you more information.
We are talking about this prescription.
About the?
This prescription, Cutts prescription.
Yeah.
So are there any conditions in which this prescription is valid and for other things you cannot use this?
No, so there is not a clear recipe. This is your model. Whatever you want to do with the model, this is the right prescription. So but of course you're right that for this type of model, I mean, I think we have the understanding by now that for equilibrium properties, it is in general a good idea, but you really have to. How shall I say that? I mean, you have to benchmark it against the results that you're getting. So if, for example, in the dispersion relation, you see that, or there is a weird thing happening there, which corresponds to I mean, the dispersion relation shows you energies as a function of the momentum. This shows you that some energies are getting very large. I mean, this could be the warning sign to say that there's something fishy happening here, and that the rescaling could do the job of bringing that down, because you get this large value because of the order n squared number of terms that you're adding up. But I don't think there's a general answer, and in the, I mean, I know I'm progressing slowly, but with the non-equilibrium that I will show you tomorrow, we will see that for some other problem, a different kind of scaling will be the relevant one, which I would not have guessed before I did the calculation at some point. So I don't think there's a clear answer, but I think you have to look at the consider the problem you're looking at, and if you get the impression that you encounter problems because of, say, diverging energies in that case, which is the divergent here, then be warned and maybe try the other one and see if you get a result that gives you more information about what you want to have. But it is it seems like such a simple concept. I think it has its intricacies. I have a few more comments and only a few more minutes, so I think I'm going to make a few more comments in the spirit of the end of last lecture, where I have another quarter of an hour. We started later, even better. Yeah, I want to make a few comments in the same spirit as at the end of the last lecture. We have this very simple result from a very simple calculation, just give you some ideas what extensions and generalizations have been looked at and are known, and then we can discuss a bit further and do non-equilibrium physics tomorrow for sure. Okay, let me make a few remarks. Okay, no. Okay, if in the so it's a Kitaev with long range hopping. I think I've made the remark before. The only change really is mu c becomes alpha dependent. Otherwise, dispersion relations and so on, everything remains qualitatively similar, and the physics conclusions are exactly the same. Then, okay, I mean, this is what we have discussed with Cutts rescaling. The mu c equals -1 exists all the way down for all alpha down to 0. Yeah, the original reference where this model, where the long-range version was first proposed, is Davide Vodola et al. Pierre L. from 2014. Right, then another comment that I've made earlier on, but I think which is important, long-range interactions in this case, so here, do not stabilize a finite T transition. So the model will not have a finite temperature transition however long you make the range. And then just a very brief comment as a remark. So I mentioned that Kitaev started to study this model because it has a so-called topological phase transition. That is a phase transition without a long-range order parameter, without long-range order in the model, but well, some other features which I'm not going to discuss here. But the comment here is just that the topological signatures or properties of this model are in some way also influenced by the long range interactions. And one example, without further discussion, I mean, in this model, one of the signatures of the topological transition is if you don't do the periodic chain that we looked at, but you look at finite, at open-ended systems, then so-called edge modes will occur. These are specific modes localized only at the edge of the system, and these edge modes decay away from the edges, usually exponentially fast, and this localization of the edge modes at the edges will, for small enough alpha, also be influenced by the long-range interactions. So there are, some of the topological signatures are affected, and there is a paper on this by Niccolo Di Feno. Yes. I would not know if this is true as a general statement. They are not in this case, but I mean, so in this case, the topological signatures, or the quantum phase transition is a topological one, so it is between a phase with one sort of topological properties and another phase. And if you don't lose the phase transition with the long-range interactions, I don't see how the topological features would be washed out. They may change, but they should not in any way like disappear or become irrelevant, as long as you don't lose the presence of a quantum phase transition at that point. I would not know of a model where this happens, where you lose it. Yeah.
That implies long-range interactions do not usually, like, what should I say, remove the phase transition.
I would not know of a single model where this happens, but look, it's not a field where everything has been explored and all properties are known. I mean, maybe someone comes up with a model where this happens, but I haven't seen anything of this. So either it enforces a phase transitions or stabilizes it, or it does not change the existence of a phase transition, but just some properties like critical exponents, as we have seen. So, well, at least in the models that have been considered. All right. Sorry? No. Sorry, I have the feeling I'm not in a good shape today. Yeah. Sorry for that. This is what you meant, right? Yeah, yeah. This plot, this is just an analysis of the dispersion relation in this area for different values of alpha, and this is in a log-log plot, and this is only, I plotted for, well, first myself to see and then also for you, that they are the larger values of alpha where the slope here does not change, which corresponds to the exponent not changing when alpha is varied. It remains 1. And then there is the regime of smaller alphas between 1 and 2, where when you change the value of alpha, you change the slope of, I mean, this is the dispersion here close to 0. You change the slope, so you change the critical exponent. This is only numerically plotting this function on this scale and seeing with the bare eye that the critical exponent changes with alpha, meaning the slope changes, and in this regime the critical exponent doesn't, the slope does not change, so the critical exponent does not change.
From alpha equals to 1, you are having a gap.
Yeah. So I plot here values starting from alpha equals 1 to larger values. So there's always, the gap is always closed. And I plot just an asymptotic region around here on a log-log scale, and I see the slope changes, and at some point gets stuck, and when I make alpha even larger, the slope is not affected anymore. It's really just a visualization, if you want, of this behavior here, where the z is the exponent that is changing, and at some point not changing, and this is the corresponding power law plotted.
Alpha equals to 1 is constant. Alpha equals to 1.
Yeah.
It's constant. So it's not going to 0. It's not going to.
Yeah. You may see from alpha equals to 1 to smaller values of alpha. No, this I don't remember what the asymptotic was in that case. So I said when preparing this here for the lecture, I did not. I should have also done the model with the Katz prescription, but I didn't. So I didn't check what happens when you make alpha smaller than 1 in this case. Yes.
When we are talking about the phase transition,
Yeah.
so what phases does this transition separate actually? So what are the different phases that we are trying to see?
Now this is a bit. Now I'm trying to remember how this went. So what Kitaev did in his original model, and I think the discussion you can do for the nearest neighbor case, it does not change to my knowledge too much, it becomes technically a bit complicated. So I think when you what he does is he takes the fermionic representation and writes the model in terms of so-called Majorana fermions, and then in this representation, each of the original fermions corresponds to 2 Majorana fermions. So you need 2 Majorana fermions to represent one of the original ones. And then if you write the chain in the Majorana fermions, then there is you have the 2 phases correspond to whether the Majoranas within one site are essentially oriented or are, no, how did this go? I think have this, well, there's some, whether you have some properties within this pair of Majorana fermions that correspond to 1, or across between 2 Majoranas that are belong to 2 original fermions. And you have both possibilities as the states, but you cannot easily go from one to the other. So, sorry, this was a bad explanation, but it also gives you the picture that if you connect, if somehow the Majorana of one side and the next one are connected, then you may have the ones at the end of an open chain which don't have a partner. And this was a bad explanation, but in this language, when you transform the chain to another representation, you can get a kind of visualization of this thing. Otherwise, there is, of course, the connection to the original transverse field Ising model, where you can say the order parameter of the transverse field Ising model transformed in the fermionic language is a quantity that also tells you something about what the 2 phases, how the two are distinguished. And then I believe, as always with these topological phase transition, you have a way of constructing topological invariants, like quantities that you can where you can assign say a plus or a minus number, but I don't remember how this went for this model. Sorry, this was not a good explanation. I tried. I have, I would finish this off with just the short reminder of what I believe the main points of this, our study of equilibrium properties now were, like both today's and yesterday's lectures. And I think just as a summary, if you remember only 3 sentences from what long-range systems can have as special properties. So let me say this as a short summary. I think the one main observation is that mean field becomes exact for alpha between 0 and d in the thermodynamic limit then I would say the second important one is long range can stabilize phase transitions, meaning the long range model may have a phase transition when the short range model does not. And universality classes, or in other words, critical exponents, are affected by long-range interactions and may change continuously with alpha. Yeah, I would think these are the main points where I would say the strongest differences between long-range and short-range systems in equilibrium physics.
Why are you saying the second line that long range will stabilize this tension? Because increasing the alpha will completely wash out the quantum phase transition.
No, increasing alpha, you do not. No. So sorry. This stabilizing, we did not observe in the quantum phase transitions today. Yesterday, when we looked at thermal phase transitions, we saw that for at finite temperatures for sufficiently small alpha, we do have a thermal phase transition in the transverse field easing model or in the Heisenberg model, whatever. And for larger alpha, so for shorter range interactions, we do not have a phase transition in a 1D transverse field easing chain. So 1D transverse field easing chain with nearest neighbors, no thermal phase transition, and only for alpha smaller than 2, long range is strong enough to stabilize the phase transition, and then you have 1. This is what I mean with this statement here. In here, we did not see a difference in terms of, we have a quantum phase transition, whatever the value of alpha is, and I don't know of a way of saying, well, it's stronger or weaker. I mean, sometimes people would say, depending on the critical exponents, if a certain critical exponent is larger, then a divergence is sharper. You may call it stronger, but I wouldn't make this distinction here.
Above, when alpha is smaller than half, then or smaller than 3/2, then the usual gap closing quantum phase transition is not happening, isn't it?
When alpha is smaller than 1, then yeah. So, I mean, these values I only used as representatives of the corresponding integer intervals, if you want. So 1/2 here for me is the representative for alpha between 0 and 1, where you'll have the divergence. But this is just to plot some number, some choice. Alpha 3/2 is my representative for alpha between 1 and 2, where you go down to 0, but you get this very sharp feature, and the other ones are for alpha larger than 2 in this.
0 to 1, there is no quantum phase transition.
at the
alpha between 0 to 1.
yes. So here, because this guy is not going down, there's no quantum phase transition, and this was the story I'd say. This is, as we discussed a little bit, we failed to have a quantum phase transition because we did not do the cuts, did not include the Katz factor. If we would have done this, we would have seen that it goes down to 0 as well. Yeah. I thought it was like from a pedagogical point of view a good idea to not include it and then discuss the non-inclusion, but I have the feeling that it didn't turn out so well, so next time I would do it, I guess I would do it differently, but anyway. Do we have more questions?
Can you comment a bit about how topological signatures have influenced?
Topological signatures. So the only one I know is what I briefly mentioned, that one of the possible topological signatures, there is not only one, but there's different things you can look at, is in an open chain are the edge modes, which are localized modes like close to the edges of an open chain, and the degree of localization is affected by the long-range interactions. This is the only effect I know. But this is also, again, this is an underexplored topic. It's not that this has been studied in many models, in many variants. So to my knowledge, topological phase transitions in long-range models, I think this is the model that has been studied. I don't know of another one really. So there is not so much known yet. Yeah.
Okay, so do we have any more questions? Let us then thank Mikhail and
thank you.